Most of our knowledge about giant exoplanets comes from a convenient alignment. When a massive, scorching gas giant orbits its star in a tight circle, it regularly passes in front of the stellar disk, blocking a tiny fraction of light. This transit method makes them predictable targets. But the cold, wide-orbit planets that actually resemble the giants in our own solar system almost never transit their stars from our perspective. And if you try to photograph them directly, the faint glow of the planet is immediately lost in the overwhelming glare of its sun. This creates a detection gap for worlds like Epsilon Indi Ab. Sitting just 12 light-years away, this superjupiter is roughly 275 Kelvin, chilly enough for water to freeze. We knew it existed for 2 decades because its gravity tugs on its host star, yet its actual appearance remained a mystery. Spotting Epsilon Indi Ab is a technical milestone. It represents the first time we can move beyond detecting mere gravitational wobbles and actually observe a true analog to our own outer solar system. Capturing that image required the James Webb Space Telescope. Its primary mirror is designed specifically for extreme infrared sensitivity, allowing it to pick up the faint heat signatures of objects that are essentially invisible to ground-based cameras. MIRI achieves this through a coronagraph. By placing a mask in the optical path to block the star's light, it creates a high contrast zone. This successfully isolated the thermal signature of Epsilon Indi A, providing the first direct image of a cold gas giant. With the image captured, the data was finally available to read the chemical secrets of a world that has been cooling for billions of years. For 30 years, astronomers have relied on a specific set of atmospheric models to predict what planets look like at these temperatures. According to those trusted cloud-free calculations, a world as cold as Epsilon Indi Ab must be enveloped in a thick, dominant layer of ammonia gas. To find it, the researchers utilized 2 specific filters, at 10.6 and 11.3 micrometers. Because ammonia absorbs light at 10.6 micrometers, the planet's brightness should drop significantly there, while remaining high at 11.3. But actual Webb data showed only a minimal difference. The massive predicted ammonia signature was missing. The high-precision mid-infrared data reveals a persistent tension. Our long-standing chemical models cannot explain why the ammonia signal is this weak. This discrepancy forced a rapid elimination of conventional theories. The first hypothesis suggested that Epsilon Indi Ab might be a low metallicity world, naturally lacking the heavy elements needed to form complex molecules. However, archival ground-based observations rule this out. A low metallicity planet would shine brightly in the near-infrared, between 3 and 5 micrometers, but Epsilon Indi Ab is surprisingly dark there. The second hypothesis explored nitrogen depletion, the idea that the planet simply didn't accumulate enough nitrogen during its formation to produce ammonia. To match the Webb data, nitrogen levels would have to be depleted by over 90%. This completely contradicts our current understanding of how giant planets accumulate their thick atmospheres from a protoplanetary disk. Instrument error was also dismissed. The MIRI coronagraph data was collected across multiple epochs and remains consistently clear. If the chemistry follows the rules and the data is pristine, then the ammonia must be present, meaning something in the atmosphere is actively hiding it from our view. The research team at the Max Planck Institute realized they had to rethink the physical structure of these massive planets. Reconciling a muffled ammonia signal with a planet that is also dark in the near-infrared requires a physical barrier. The data points toward the existence of a high-altitude lid. These atmospheric layers are incredibly complex to simulate, and most published models omit them to simplify the daunting mathematics of planetary evolution. Deep in the freezing upper atmosphere, a violent weather system of thick, patchy water ice clouds is likely choking out the outgoing light. These clouds act as a physical mask, hiding the ammonia below and forcing a total rewrite of our atmospheric models.
12 light-years from Earth, if you plunge into the exoplanet Epsilon Indi Ab, you hit a violent, churning wall of freezing water ice. This world is a superjupiter, holding 7.6 times the mass of our own Jupiter, yet it stays bitterly cold, hovering just around 275 Kelvin. Astronomers measure cloud density using column optical depth. While a thick cloud layer on Earth might register in the dozens, the ice ceiling here reaches a value of 416, a density making the atmosphere nearly impenetrable. This massive deck is a planetary vault. It traps internal heat rising from the core, scattering light and muffling the signature of ammonia buried beneath the ice. From deep space, the planet appears deceptively quiet, but in reality, it is a churn of thermal energy trying to punch through a colossal frozen lid. This ice fault explains the mystery of the planet's missing ammonia, but it also reveals a significant flaw in our established rules of planetary physics. To see this detail from 12 light-years away, astronomers turn to the James Webb Space Telescope. Direct imaging of a cold planet next to a bright star requires engineering of extreme precision. Webb's massive mirrors are designed to capture the specific, faint, mid-infrared heat leaking from the planet's atmosphere. The telescope's MIRI instrument compared the planet's brightness at 10.6 and 11.3 micrometers. Because ammonia absorbs light at one wavelength but not the other, the resulting gap provided the footprint of the gas hiding under the clouds. We can now see Epsilon Indi Ab as a complex dynamic weather system that is actively pushing our best observational technology to its limit. According to decades of astrophysics textbooks, these specific ice clouds were not expected to be there. For years, theorists used a cloud-free mathematical grid to predict gas giants, assuming a clear, predictable atmosphere. Simulating how ice particles actually condense, swirl, and scatter light across an entire planet simply requires an impossible amount of processing power. Astrophysicists took a deliberate scientific shortcut. They stripped clouds out of the math entirely to save time and processing capability. Webb's new data proves this shortcut is insufficient. The old math fails to account for the thermal reality of cold, temperate worlds. Epsilon Indi Ab's frozen decks prove that clouds alter a planet's infrared signature too severely to be ignored. Theorists are now forced to factor in high metallicity and unusual carbon-to-oxygen ratios. These are variables that do not easily fit into our standard theories of how massive planets form. This discovery has triggered a rush within the astrophysics community to start rewriting the foundational code we use to simulate exoplanetary science. Clouds are the dominant feature of this planet's reality. They can no longer be treated as an optional variable in our simulations. This shift in how we model gas giants is a prerequisite for the most ambitious goal in astronomy: finding a second Earth. True Earth analogs are cold, temperate worlds shrouded in complex cloud systems. If our models cannot accurately interpret the massive, thick ice clouds of a super-Jupiter 12 light-years away, we cannot hope to read the delicate, thin atmosphere of a small planet at much greater distances. This gas giant is the mandatory proving ground for our entire search for life. It is where we must perfect our ability to see through the haze. The next stage of this technological evolution is the Nancy Grace Roman Space Telescope. While Webb measures the internal heat glowing from the planet, Roman will hunt for something different: the glint of starlight directly reflecting off those alien cloud decks. By benchmarking our technology on Epsilon Indi Ab right now, we are calibrating the instruments that will one day search for an Earth-like albedo. We are working through the difficulties of reading the weather on hostile Jupiters today so that we can recognize a habitable world tomorrow. When an Earth-like world finally crosses our lens, this shift in our understanding will ensure we are actually ready to see it. I'm Veriflux. Thanks for watching.
Thank you for watching.